record. Did I record? Okay. All right. Well, I hope it's working. Let me bring up another chat screen here. I don't see where the hell this chat screen is. All right, there's the chat screen. So could somebody write on the chat screen if you can see the mathematics here on the left? That is to say, the mathematics where my pointer is moving. Could somebody type on the... Okay, good. All right, so I've got a number of things to do today, and I think what I'll do is I will start with curvature. I've redone the section on curvature, and let me just remind you how it works. The basic idea is parallel transport, which means that you take a vector and move it along a curved surface in such a way that that the way the vector looks in the tangent space remains constant, remains fixed. And so that means that the dot product of the change in the vector with the cotangent vectors vanishes, and that amounts to the vanishing of the covariant derivative. And so the criteria or the criterion can be written either this way or that way. In terms of a cotangent vector, it looks this way. In terms of a tangent vector, it looks like that. So basically, the nth derivative of the ith component dotted into the displacement dxl, the change of the coordinates is the same thing as this Christoffel symbol summed over k times vk, again, times dxl. And a picture of it is, as usual, worth 1,000 words. You can take a tangent vector and move it along the equator this way, and you're not changing it all, and so you're transporting it in a parallel way. But now when you move it up the longitude, say longitude 0 up there, what happens is, because the Earth is curved, it winds up pointing in that direction up there. Oh, God. And now if you go to this picture, this red arrow is equivalent to the green arrow, and as you parallel transport it down a different meridian, a different line of longitude, which might be called a meridian, and get to the equator, it looks like this green arrow here. And if you parallel transport that back, you see it's perpendicular to the original red arrow that you started with. And so that's an example of parallel transport. Now, what I've done is I've rewritten the curvature section, and I'll post that on the class webpage tonight. Anyway, if we're parallel transporting a vector, a covariant vector VI around a loop DXL, then if it is to be parallel transported, it's the change in the vector is going to be given by this. This is because I'm using this formula here, that the change in the vector is the Christoffel symbol dotted into the vector like that. Okay, so just copying that basically, and every now and then one needs to change the indices, the labels of the indices, and that in general relativity, you have to keep track of the indices. Normally they take care of themselves, but you've got to keep track anyway. Anyway, on the curve, what we're imagining is we're going to go around a little square, a very tiny square of side A. And on the square, we're going to approximate the Christoffel symbol by the value at the center of the square plus the derivative of the Christoffel symbol times the distance from the center of the square in the nth direction, and then summed over n. And the same thing for vk. It's going to be vk at the center of the square plus the nth derivative times the nth distance from the center of the square. And so now, though, we're saying that the change, this nth derivative isn't any ordinary nth derivative. It's the nth derivative to make the transport parallel, and that means it has to be equal to gamma m Vm sub kn. And so that change then of the Christoffel symbol times the covariant vector integrated around the little square is going to be an integral of these two terms, where I'm going only to first order. And then first notice that the integral, and here I'm going to start using the integral of anything dxl is 0 because it's a loop. So you're going back to you're going back to 0. And so that's that integral is 0. So when we put the gamma, this gamma, and this v in there, we get to lowest order these terms. And then the gamma times the v just integrates to 0 because of this equation, this equation. The next two terms are vk times this guy plus gamma times that one. And so that's these two. And then I'm dropping the term that's quadratic in x minus x0. Okay, now, and also v, gamma, 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 and v, they're all evaluated at x0, the center of the square. So that's what we've got to do. Now, this is confusing, and so let me try to demystify it. So the integral x minus x0, say to the n, dxl, it turns out that this is plus or minus a squared. Well, it's plus or minus a squared, and whether it's plus or minus depends upon which way you go around the square, and so that's not really important. The important thing is the magnitude. So let me just show you as an example here. So let's take the square, and I think I'm going to shift to blue now. Here's the point x0. This distance is a. This distance is also a. And I'm going to integrate around the square. Okay, and what am I going to do? I'm going to integrate let's suppose this direction is the x direction and this direction is the y direction. Okay, so I'm going to be integrating around the square, and I'm going to be integrating what? I'm going to be integrating the distance. Let me say x minus, the center of the square is going to be at a over 2, and I'm going to be integrating dy. So in other words, I'm setting L, XL is going to be Y, and XN is going to be just X. So we're in the XY plane, basically. And now, if we do this integration, well, we're going to integrate around the square. So at first, we go this way. In the, let us say from 0 to A. Okay, so if we integrate from 0 to A, we're integrating, well, the integral is dy. So dy is going from 0 to A. That's just A. And what is x? Well, x is going to be, let me try to get this straight. We are integrating, we're integrating dy, so we're going up this axis here. This is so we're going up the y-axis, and on that y-axis, x is equal to a. So this is a minus a over 2, and dy is a. The integral of dy is a. So let me point out here, the integral along here, dy is 0, so that doesn't contribute. And the integral along here doesn't contribute also because dy is 0. But then we go down this way, and now the integral of dy is minus a, and the value of x is 0. So this is minus a over 2. So we add the two together, and we get a squared minus a squared over 2 plus a squared over 2 equals a squared. So that's what this thing means. You see, it's actually very simple, but it's confusing because, first of all, it's a line integral, and it's not the kind of line integral that we see in electrostatics when we integrate E dot dx. Here, we're integrating something that's not really a dot product. We're integrating x, and we're doing a dy integral, and the dy integral is just up the y-axis at x equal to a, and then down the y-axis for x equals 0. And on the other two sides of the square, dy is 0. So that's how it works. So this thing is plus or minus a squared, and it's 0 if we were integrating in the same direction. So maybe I should do that in particular. So let's do the integral. Now, I haven't actually thought about this. So let's do the integral. Let's make that x still. And so I'm doing this live. I haven't prepared this. I haven't done this integral in probably 10 years. So we're integrating this thing. So that's an integral, let us say, from 0 to a of x minus a over 2 dx. So that's the integral this way. And then we have to do the integral that way. And so plus the integral from a to 0 of x minus a over 2 dx. Well, I think we're done because that's obviously 0. let me first make this a little bit neater. So the integral from 0 to a of something plus the integral from a to 0 of something is equal to 0. So we just get 0. So that's why this thing is 0 when n equals L. All right, now back to the curvature business. So what we've got is that the change in the covariant vector v, when we parallel transport around this little loop, here it's just generally a loop. But now if we say it's a square, then this x0, x minus x0 n dxl is plus or minus a squared and 0 if, well, it's anti-symmetric in n and L, and it's 0 if n is equal to L. And let me see, I didn't make it clear that it's anti-symmetric. So let me just make sure that we are, let me just show why it's anti-symmetric. I just said it was obviously anti-symmetric. So I'm going to switch back now to maybe red. And instead of doing the xy integral, I'm going to do the yx integral. So y minus a over 2 dx around. And now I'm going around the square. And now going dx, again, I'm going to go, well, I'm just going to go the bottom one and the top one. So I'm going to integrate along here and then integrate along there. So what is y on this integral? Oh, Christ. Sorry, I don't know. Congress, of course, is bribed by the people who make these spam calls, and so they permit it. That's what's actually going on. Anyway, we're going to, what is the value of y on the bottom axis? Well, it's 0. So it's going to be an integral from 0 to a dx of minus a over 2 dx, and then plus an integral from a to 0 when y is equal to a, so a minus a over 2 dx. Okay, so the first, this integral here is going to be minus a squared over 2, the first one. The second one is going to be minus the integral 0 to a of, and this a minus a over 2 is, oh, God, is just a over 2. And so this is a squared over 2 minus a squared over 2 minus a squared minus a squared. So indeed, the integral y dx, y minus y0 dx is minus the integral of x minus a over 2 dy. We got a squared for that one. We get minus a squared for this one. So I verified the anti-symmetry. And there's nothing going on that's more mysterious than that. Now, if we go back to this expression here, then what we do is we see that this thing is, the integral is an overall factor of a squared. The vk, we're going to replace m by k here. I should have done that earlier. I don't know why that was sort of silly. Anyway, so that we have a vk that we can factor out. And when we factor out that vk, oh, I did it here. All right. So in other words, I'm taking this expression here and doing this for the x minus x0 n dxl, and I'm interchanging m and k. M and k are both dummy indices here. And so when I do that, I get a squared. Epsilon NL is just plus or minus 1, and 0 if n is equal to L. And what remains here is this term plus this term. And that then is equal to this when we've interchanged M and K. And so this is this has to be still summed over L and N, and we do that. When we do that, we get A squared, and then we get the INL term minus ILN term, and in other words, we get this term twice, once with a minus sign. And so the change then in the covariant vector is the area of the little square times this structure involving the Christoffel symbols, and then it's all, so to speak, dotted into the covariant vector. And the thing inside the curly brackets is Riemann's curvature tensor. So this is a better derivation of Riemann's curvature tensor. It's explicitly anti-symmetric in the last two indices because those last two indices came from epsilon NL, which, as we just saw explicitly, if you do the x dy integral, that's minus the y dx integral. And so that's what that is. Okay, and then there are various symmetries that reduce the number of indices from 256 down to 20, which is pretty amazing. And then the Ricci tensor is then you raise one index and contract, and the Riemann scalar as you contract again. I thought I should say something about the scalar densities here. The basic idea here is that it's something that we were talking about way back in chapter 1 on Jacobians. Remember that the area is the Jacobian. If you change variables from x's to y's, the change is a Jacobian. So the volume in terms of the volume of a dy of a, I guess it's a parallelepiped. No, I guess it isn't that. It's a volume with sides dy1, dy2, dy3, all being vectors. It's then a determinant of the actual Euclidean space coordinates with respect to these y's and times the y's. And so the volume elements go as Jacobians, is I guess the way to say. dxn is the Jacobian of the x's with respect to the y's, dyn, and the Jacobian is this thing here of derivatives. And so if we can transfer all that to why it is that in general relativity action integrals, one always sees square root of g or square root of minus g in most books, but I use little g as the absolute value of the determinant of the metric tensor. And it's the metric tensor that's the covariant rank 2 metric tensor, so lower indices. And the idea here is that we want d4th x square root of absolute value determinant of gik. We want that to be the same thing as when we change variables, d4th y square root absolute value of the determinant of gik, but here in terms of the y variables. And so the deal is that we can say that d4th y is a determinant of partial y partial x. And on the other hand, the square root of the determinant of, I'm sorry, I got that actually wrong. So let me fix that. It's actually d4th. Well, I'm doing this one. d4th y, in other words, d4th y is d4th x times the determinant of partial y partial x. And then the determinant of gij in the x coordinates compared to the y coordinates is partial xi partial y. Actually, I had a j here, so let me just keep it straight. Partial xl partial yk g jl of x. So it looks like this. And this is here we have a square root, and there's actually a determinant here. So this is really a determinant of all this. And so this is a product of three determinants, this one, that one, and this one. And so altogether, this then is d4th x, determinant of partial y partial x, determinant, whoops, hold on, determinant of partial x partial y, and then d4th x, and then square root of determinant, absolute value determinant of g of x. And so these two determinants cancel, and what we get is d4th x square root of absolute value determinant g of x. So in other words, it is a scalar. It's the same thing as d4th y square root absolute value determinant g of y. Okay. So that's why we have this, and the way I write it once again is d4th x or square root of g d4th x, because I use g as the absolute value of the determinant. Okay, so let me see. I wanted to. Okay. One other thing about the homework, there's a problem due, I guess, tomorrow, problem 13.14. I neglected to say that you're working in Euclidean 3 space. So in problem 314, you're supposed to be thinking about Euclidean 3 space. So let me just show you that. So consider the torus in Euclidean 3 space with coordinates such and such and so forth, and then find the basis vectors and the metric tensor. So I'll leave that aside. So that's done. So there are these different things that I wanted to do today. And now I'm going to do two problems that are like homework problems, in particular 13.2. I'm going to do 13.2, and instead of doing it in real time, I'm just going to show you the solution. So here's the problem. So use the flat space formula. Let me move this over. dp is x hat, that's a unit vector in the x direction, dx plus y hat dy plus z hat dz. So this is just obviously flat space change in the point. To compute the change due to d rho, d phi, and dz, and derive expressions then for the orthonormal basis vectors rho hat, phi hat, z hat. And I mean, this is really just vector calculus. You probably had this as sophomores in college. But anyway, so dp is this. So what's the basis vector E rho? The basis vector E rho is partial P partial rho. Now x is rho cos phi. We're in cylindrical coordinates here, okay? Y is rho sine phi. Let me maybe just in case some people haven't seen some of these things. So in other words, that's the z-axis. This is the x, y, z-axis, and the angle here is phi, and rho is the distance here, so that's rho, and z is how high you are. X is rho, and it's cosine theta, so we cosine phi, I should say. This is the angle phi. And y is rho sine phi. I don't know if, actually, I'm not sure that one is really perpendicular. So let me make it like that. All right, well, I don't know. Anyway, x is rho cosine phi, y is rho sine phi. So dx is cosine phi d rho, if we're just changing d rho here. Y, the change in y is sine phi d rho. So dp, in terms of d rho, is x dx, and dx is cosine phi d rho. Y dy, dy is sine phi d rho, so it looks like this. So the basis vector rho hat is x hat cosine phi plus y hat sine phi. And we don't need to normalize it because it's automatically normalized. The basis vector E phi is the derivative of the point with respect to phi. Dx is minus sine phi d phi, because if you are doing d phi, the derivative of the cosine is minus the sine, derivative of sine is the cosine, so we have dy is cosine phi d phi, or d phi. So dp is minus, is x hat dx, which is minus phi d phi, y hat dy cosine phi d phi. So E phi is minus x hat d phi plus y hat cosine phi. Again, you don't need to normalize it, that's phi hat. And Ez is partial P with respect to Z, and that's just Z hat. Okay, so that's problem 13.2. You need these formulas to do the rest of the homework, although of course you can derive them or invent them yourselves. You don't, it's not really necessary for me to do that, but I did it anyway. Okay, now I'm going to skip to a much later problem here. I'm going to go to problem 13.28. And this is just, I think this is intrinsically interesting, and especially for those of you who are interested in cosmology, which is, what we hope to get to later in, we've got another week or so of this course, and a week or two, and so I'm going to hope to get through the cosmology part. So, yeah, I think I'll just go to the derivation in right here in this. It's okay. So the idea is to, so this is the actual solution, in other words. So the idea is to, or the problem is to embed these points in the, or the points are already embedded in this flat semi-Euclidean space with this metric, and we want to derive the line element and the metric. Here are the points. These are the coordinates of the points, or this is the point in this 5-dimensional space with this metric. And so to get the unit vectors, we just differentiate. We differentiate this expression with respect to t, and I must say I'm a little puzzled here as to what happened. Oh, I'm sorry. The AL's cancel. So when you differentiate with respect to t, you just do get c. But now if we differentiate with respect to chi, or key, we have it occurring in sinh, and cosh. Well, derivative of sinh is cosh, so we just get this whole, we get a 0 for the first entry, and then we get cosh chi sine theta cos phi, cosh chi sine theta sine phi, cosh chi cosine theta, and sinh chi. So that gives us this vector E chi. To get E theta, we differentiate with respect to theta, and we get cosine theta here, cosine theta minus sine theta, and 0. So that gives us this vector. And then if we differentiate with respect to phi, we get a sine phi here, cosine phi there, and zeros. And so we get 3 zeros, and then these terms. Now, this flat 5-dimensional embedding space has a metric with 2 minus signs. So when we form dp squared, we have to take the dot product in this way. And maybe I should do this explicitly. So what is this dp squared? Well, first it's going to be et dot et. Let's see. First, I think we can sort of see that this guy's orthogonal to all the others. And in fact, this one's orthogonal to that one. These are all orthogonal vectors. So this thing is, so the metric is going to be diagonal, and we only need to take et dot et, chi dot e chi, theta dot e theta, e phi dot e phi. So this is et dot et dt, God, my writing is just dreadful, plus e chi dot e chi d chi squared plus e theta dot e theta d theta squared plus e phi dot e phi d phi squared. And now et dot et, well, there's a minus sign here. So this is minus c squared dt squared. The next one is this dotted into itself. But now when we dot this, we're going to get a sine squared cosine sine. So let me try to see if I can do this in my head here. We have sine squared. Let's do the phi part first. Cosine squared phi, sine squared phi. So we basically just add these squares. And then we have sine squared theta, cosine squared theta. So we get a cosh squared. And then we have a sinh squared. But the sinh squared comes in with this minus sign. So we get minus sinh squared. And so that gives us plus a squared L squared times cosh squared chi minus sinh squared chi. times d chi squared. I find CH squared to be and SH squared to be adequate abbreviations for Koch and Cinch. It's the Russian usage, by the way, because in Russian they have letters that are like CSH and SCH. I studied Russian, but so long ago that I don't remember the details. Anyway, they have letters that they use, and so that when that stuff is transliterated into English, we just get SH, and CH. Anyway, E theta dot E theta. Well, it's the same business. Now we don't have to worry about the minus signs because those components are zero. So we just get cosine squared phi, sine squared phi, that adds up to 1. Cosine squared theta, sine squared theta adds up to 1. Sinh squared plus sinh squared adds up to 1. So basically we've got here just plus a squared L squared sinh squared key d theta squared. And then the last term is this one, E phi dot E phi. Again, we don't need to worry about the metric. We get the sine squared plus cosine squared is 1. We get sine squared and sinh squared. And so what we get is, for this one, what we get is a squared L squared sinh squared chi, and then we wind up with a remaining factor of sine squared theta d phi squared. And let me just fix this a little bit. And so when you add them all together, you get this expression here. So let's see what's going on. Well, what's going on here is that this term cancels this term. And so then we finally have, wait a minute, what did I do here? No, what I just said was completely silly, okay? I just did something. Obviously, you can't cancel d chi squared with d theta squared. What you do is you combine this sinh squared. There's a sinh squared term, and so you combine the d theta squared with sine squared theta d phi squared. That's what you do. And then Koch squared minus sinh squared is 1. So this gives us this term. And then you have that term. Then, so that's what you've got in terms of chi, theta, and phi. Now, the variable chi can be reinterpreted. And what you do is you say L sinh of chi is set equal to R. dr is L Koch chi d chi. So d chi is dr over L Koch chi. But Koch chi is square root of 1 plus sinh squared chi. Sinh squared chi, well, sinh is r over L, so that gives us dr over L square root of 1 plus r squared. So you get, instead, the advantage of going from chi to r is that you get rid of these hyperbolic functions and you just have an r. So now the metric looks like this. dp squared is minus c squared dt squared plus a squared L squared dr squared over 1 minus k r squared, and then this expression here. And well, this is the metric of, this is the Robinson-Walker metric, in which instead of A, I have A times L, but A is just the basic size, the size of the universe, and so it's, I mean, either way is, they're equivalent expressions. And so this is the metric for, this is the k equals -1 metric, and so this is the metric for the closed universe. So the closed universe then looks like this. Now, actually, my memory is that there may be a typo here, because my memory is that this metric is the metric for the open universe as opposed to the closed universe. And the closed universe has 4 plus ones here. Right. If k is -1, this is all right, let's just so all right, let me just try to get this straight. We have d chi-squared, which is dr over 1 plus r squared. So k is, if it's minus kr, k is -1. And if k is -1 and we have a minus k, then this is the closed universe. Okay, this sort of surprises me. I thought that when you embed the open universe in 5 space, you get 2 minus signs. So anyway, I think I'll oh, here I've done well, I'm doing non-standard embeddings. That's what we've got here. That's why it's a little bit odd. All right, well, never mind. So let me take this away, because these are all the solutions. So I've basically done the main things that I wanted to do today. Remember, in an earlier class, we worked out what the divergence is of a tensor, and we saw that there was one could perform a certain simplification. And for the case of the energy momentum tensor, which is symmetric, we get this expression here. I guess I'll go through the covariant Laplacian. That's again uses this nice expression for the covariant divergence, where we have this. We can write it as the ith derivative of, and then we have the square root of g, and we raise the derivative index and divide by square root of g. Oh wow, that's so let me switch here to this one. All right, and let me go back to so those things that I just showed you were derived here in this section, and so let me make this much bigger. And maybe it's worth mentioning them again. So the covariant divergence, well, it's you just are doing the covariant derivative of a contravariant vector, and what you do is you just have an index that you're summing over. It's the i's here, and so then you sum over I, but you also sum over k. But G is symmetric, and so this particular sum is simpler than one would think. Namely, two of these terms cancel. The last two terms cancel because well, it's a little bit involved because it involves the GIL times GLK, and GIL GLK comma I, well, that's going to be the same thing as GLI. And now what did I? Okay, to go from there to there was the interchange of I with L without using the symmetry of the metric tensor. If you now use the symmetry of metric tensor, you get this expression, and then this is the same as that times that, and so these two terms cancel, and you just have this term. And so that is 1/2 GIL GIL K. So this structure here is simpler than it looks, and it's just equal to that. And then you use the tricks for the determinant. The determinant is the sum over I of L of the, you go across a row or down a column, and you use the, you multiply by the cofactors. On the other hand, the cofactors are the derivatives of the determinant with respect to the elements of the determinant, and the inverse of the metric tensor is the metric of, is transpose of the metric of cofactors divided by the determinant. And so that's 1 over the determinant. And then this thing is, we use this formula to get partial of the determinant with respect to the element. And then you finally find the derivative of the determinant is the derivative of the determinant with respect to a metric. Well, it's obviously the derivative of the determinant with respect to a metric, to an element of the metric, times the derivative of the element of the metric. And then using the previous formula, we can rewrite that as the determinant times the inverse metric times the derivative of the metric. And on the other hand, we already derived this expression. And so now we notice that this occurs here as well as there. And so this thing is then related to that. And so it's the derivative of the metric divided by the determinant with a factor of 2. And altogether, then, if you go from determinant to square root of determinant to get the factor of 2, that's all that's happening here. This is actually a simpler expression, but this is somehow more useful because square root of g keeps occurring in these formulas, because square root of g times d4 x is invariant. Anyway, what we get then is the determinant, the divergence, the covariant divergence of a contravariant vector then is, it's given by this. We've got a formula for this, namely that, and then combining the two, we can write combine the two like that. And that's that gives us an expression for, that gives us a way of writing Maxwell's inhomogeneous equations. In other words, Gauss's law, del dot E equals rho. Let's see, del dot E equals rho. And then the other one that's more involved, involving magnetism, it occurs in here as well. And they're all written in generally covariant form this way. Now, and if we go from curved space to flat space, replacing G by just the number 1, we get the standard Maxwell form of which is correct, which is invariant under Lorentz transformations, but not under general coordinate transformations. And then, as I said, well, all right, I did this already a little while ago. And then if you use these same tricks, you get that the covariant Laplacian looks like this. So this is I mean, it's really the same business. It's the derivative of a contravariant vector. But if the contravariant vector is itself a derivative, then what you have is in other words, the contravariant vector now is the contravariant derivative of a scalar, and that then is what we call the covariant Laplacian. Okay, this is a good time maybe to describe some things involving the principle of least action. The invariant proper time for a particle to move along a path, well, it's an integral, we say detour, and we make it invariant by writing detour in this way, minus and GIL dxi dxl. You see, if the particle were just sitting there and not moving in space, this would just be dt squared, and this would be g00. And so this would be just dt squared, and if we're in flat space, g00 would be just -1. Minus sign would cancel. I've left out well, it'd be a c squared, which cancels there. I don't know if we need to actually go through this. This was maybe a little more complicated than necessary. But what one winds up with is an equation for a particle, a free particle, in a gravitational field. So it's worth going through, but maybe I'll leave it. If you want to go through it yourselves, you can. What you wind up with is the equation for a particle moving in a gravitational field, and it's the second derivative of the coordinates with respect to tau squared, and then the Christoffel symbols and a quadratic form in the ordinary derivatives. And here I need to remind us what detour is. Detour is just this invariant, this generally covariant time or element of time. So it turns out that the equation of a freely falling particle takes its simplest form when you don't have a t here, but a tau. And the thing to notice here is that there's no mass term. So all particles, independently of their mass, fall along the same geodesics. You can, well, all right, I'm going to skip that. All right, maybe this example is worth doing. If you have a spatially flat expanding universe, so we're in flat space and it's just expanding, what is the motion of the particle? Well, it's d by d tau of GR UR. UR is dxr d tau. And that turns out to be this. And so you get a dA d tau and then an a squared d tau. And what you wind up with is that the momentum is the momentum that the original momentum divided by the scale factor. And so this just says that particles in an expanding universe, if they're not acted up, if they're just moving freely in an expanding universe, their momenta shrink, and their momenta shrink just as their wavelengths expand. Remember that the wavelength of a particle is them is Planck's constant divided by the momentum. And you may need an H, that may need to be an H bar. I don't remember whether it's H or H bar. In natural units, it's just 1 over P. There's also a simpler action principle which gives these equations much more simply. And if we now generalize to electrodynamics, you have as your action, well, first you have the invariant volume element, square root of G d4 of x, and then you have the ordinary Maxwell action. And I say ordinary, but it's not quite the one that Maxwell and Faraday invented, because if this is the Maxwell-Faraday one, this one has 2 raised indices, and you raise indices with the inverse of the metric tensor. The same thing over here. Maxwell would recognize this, but here the K index has been raised. And if you now apply the principle of least action to this expression, well, what do you get? You get the partial derivative, the derivative of this with respect to x times the change in the action, plus jk times the change in the action. And so this altogether gives us this expression here, that a sort of divergence of square root of G times F is jk. We have a scalar field, mass m, in a gravitational field. Then what we have as an invariant action is, this is invariant because it's the inverse of the metric tensor, and then 2 covariant vectors. And this is just a scalar, so this is fine. You apply the principle of least action, and you get the change in the phi, the derivative with respect to x. And this gives us then this as the equation of motion of a scalar field. And in particular, in a flat universe with an expanding scale factor, what you wind up with is phi double dot plus a dot over a. That's the Hubble rate. And the Hubble constant is this at the present time. That's the Hubble constant. Of course, it's not a constant. It's like everything in astronomy is misnamed, I guess, because it's the oldest science, and it's just burdened with so much tradition. Anyway, you have the minus c over a squared plus grad squared phi plus c squared m over h bar squared phi equals 0. So that's the scalar field in a flat expanding universe. The action of the gravitational field is this, and this leads to Einstein's equations. This, of course, is Newton's constant. Newton's constant is essentially 1 over the square of the Planck mass. So this is Planck mass squared times this. And so that means that the tiniest change in this has a huge action associated with it. And what does that mean? That means that gravitational changes are pretty small because they get multiplied by a huge factor. R is the Riemann scalar, and then G, of course, the absolute value squared of the determinant of GIK, and then you integrate. This then leads to Einstein's equations. I think I'm going to skip this and just go to weak gravitational fields. So if we take the equation for a freely falling particle in a weak gravitational field, what we would have would be the motion is slow, so we're going to neglect the velocities compared to just u0. And when we do that, we just get, instead of this expression, we just get this expression. Because it's static, we're going to ignore the time derivatives in the Christoffel symbol. And so this Christoffel symbol is just going to be the kth derivative of G00. And then because the field is weak, it's basically Gij is going to be is going to be the eta ij, which is just the metric of special relativity. Eta is -1, 1, 1, 1. That's the metric of special relativity. And then h is then just a tiny change in the metric. And so the first order, gamma's R00 is just the rth derivative of H00, and this is just G00, or just -1 or minus c squared. And so as a result, what we have is just H0 squared, and then we have the derivative. This gamma is just the rth derivative of H00. So this expression then becomes, and remember that U sub r, UR is the derivative of XR with respect to tau. So this is D2XR d tau squared is a half U0 squared, the rth derivative of H00. And of course, U0 is dx0 d tau squared times that. So for slow motion, what we have is dx, the second derivative of dx squared. We say when the motion is very slow, d tau is just c dt. So so we just get dt squared here, and so we just have c squared times the gradient of H00. So if phi is Newton's potential, then what we say is G00 is -1. I guess I'm using the metric where G00 is essentially -1. -1 plus H00, and that's -2 phi over c squared, and so H00 is this. And so what do we get? Well, the Newtonian potential then is GM minus GM over R, and we just recover Newton's law, of course. And so how weak are the static gravitational fields that we know about? The ratio phi over c squared on the surface of a proton is 10 to the minus 39. Surface of the Earth is 10 to the minus 9. Surface of the Sun, 10 to the minus 6. Surface of white dwarf, 10 to the minus 4. When you get, though, to somewhere near a black hole, it's no longer 10 to the minus 4, that's for sure. Gravitational time dilation, this is one of the most amusing things. So let's imagine dt is the time interval measured by a clock at rest in a gravitational field GIK. And that's related, and we're going to compare that to the time measured by a clock at rest in the absence of gravity, perhaps a clock at spatial infinity. So what we have then is g00 dt squared, which is the same thing as this sum because the dx is a zero. So we can write it this way. That's ds squared, and that has to be minus c squared dTOR squared. And so now then the relation is that dTOR is related to dt by this factor of g00 and well, the c squareds cancel, and a minus sign. But on the other hand, g00 we saw for gravitational field is minus 1 minus 2 phi over c squared. So the dt and dTOR look like this. So dTOR is the time at spatial infinity, and dt is the time for the clock in the gravitational field. So you see now, if you have so let me try to get this straight now. So if we're distance r from a mass m and phi is minus gm over r, this is negative. What we get is this expression here. And so the interval between ticks of a clock at r relative to the time at infinity is that. And actually, looking at this, I think I may have a mistake here, because what we do know is that the dTOR is supposed to be small. I'm sorry, dTOR is supposed to be huge compared to dt. And this one is smaller. So I somehow have gotten this wrong. All right. Well, I will straighten this out, and class tomorrow at 5:30, I will get this straight for you. I don't quite know how I screwed up 3 equations that are all 3 of them very simple, but I think this is wrong, because what we do know is that if you're in a strong gravitational field, your time slows down, and so your ticks are very slow. It's this business of 2 different clocks ticking at different ways is confusing. All right, I'm going to end the class now. We'll have a problem session tomorrow at 5:30, and so I'm going to stop sharing and ending the class.